Okay, so in this video, we're going to look at trig integrals. And in another video, I did sine and cosine. And in this one, we're going to talk about tangent and secant. Now, everything that I say about tangent and secant also applies to cotangent and cosecant. Everywhere I say secant, you can replace cosecant. Everywhere I say tangent, you can replace cotangent. The only real difference between the secant-tangent combinations versus the cotangent cosecant combinations is that when you take the derivative of cotangent and cosecant, you get minus signs. And so you need to keep track of those. Secant and tangent don't have those minus signs. And so it's a little bit easier. You will see secant tangent combinations the most in textbooks, but they will occasionally throw a cotangent cosecant at you just to see if you can generalize these same rules. But we're going to focus on secant and tangent here. Basically, the same as sine and cosine, these break down into three cases. Now, the powers that we're going to be looking for are going to be different than sine and cosine because of a couple of different factors, primarily having to do with the way the derivatives of secant and tangent are compared to sine and cosine. The derivatives of sine and cosine are just single copies of sine and cosine. Whereas when you take the derivative of tangent, you get secant squared. And when you take the derivative of secant, you get a secant and a tangent. And so that's going to play into how we have to choose how to proceed. So our first scenario is going to be if the secant is even. And the general idea here is if secant is even, regardless of what's going on with the tangents, we can pull out two of those secants to be our derivative and convert the remaining even secants to tangents, and then we will have tangents and its derivative. If tangent is odd, then we're going to try to pull out a secant and a tangent. So that's the odd tangent. And then if tangent was originally odd and we took one tangent away, the remaining tangents are now even, and then can convert those back to secants so that we have the secant derivative and then everything else is secants. And then our third case is the case if secant is odd. Now this may involve even tangents, or it may be secant is odd by itself. In that scenario, we're going to have to do integration by parts in order to make this work, but we will be able to get something. Now, hopefully those odd secants are not going to be too crazy. If it's just one secant, it's a little easier. But if it's a lot of secants, then like secant-cubed, we have to do integration by parts. If it's secant to the fifth or higher, then it's also going to be crazy, but it's going to be rounds of what secant-cubed is going to look like. All right, so we are going to need just one identity for this scenario that we have to really worry about, which is, since we don't have power reducing identities that we'll be applying as we did with the sine and cosine, it's basically just this Pythagorean identity. And again, if you're doing cotangents and cosecants, the identity is the same. It's 1 plus cotangent squared is equal to secant squared. And so that same identity will apply. All right, so let's look at our first scenario where secant is even. So as I said, the rule here is with secant even, we're going to try to pull out two secants to be our du and then convert the remaining secants to tangents. So what we're going to do is we're going to pull out our secant squared, and then the remaining secants we're going to convert via the Pythagorean identity. So our secant squared and our dx is going to be our du, and then secant to the fourth is secant squared squared. So what we're going to do, I'm going to take my secant to the fourth, and I'm going to replace it using my Pythagorean identity up here. 1 plus tangent squared x squared tangent squared x. And then my u substitution is going to be tangent, and the derivative will be that secant squared that we've left behind. So u equals tangent x, du equals secant squared x dx. And if I make that replacement in my integral, I'm going to get 1 plus u squared times u squared times du. And then I'm going to have to do some algebra, obviously, in order to be able to integrate this. So applying the perfect square rule, I'm going to get 1 plus 2u squared plus u to the fourth for my binomial squared. And then I'm going to distribute my u squared. Jumping ahead. U. And now I can do my power rule. And doing my anti-differentiation, I use 1/3 u cubed. And then dividing by 5, I get 2/5 u to the fifth. And then dividing by 7, I get u to the 7th over 7 plus c. But we're not done. We have to go back to our original x variable. And so we replace our u's with tangents. Plus c. So it's all about applying this Pythagorean identity once you identify what your antiderivative, what your du is going to be. All right, so that looks great. So now let's go on to case number 2. In case number 2, we said that tangent is odd. Now, in the case where tangent is odd, this is the preferred choice, even if secant is odd. So kind of keep that in mind. It's much easier to integrate this as if it were a secant, even though you technically do have an alternative in using that third condition. This one is going to be much easier. It's not going to involve integration by parts. It's going to work very similarly to our initial example. So in this scenario, what we're going to do is we are going to pull out a secant and a tangent. So inside my integral, I'm going to leave a secant squared behind. I'm going to leave a tangent squared behind, and I'm going to collect a secant x and a tangent x to be my substitution. So that means this is the derivative of secant, and so all remaining tangents have to get it converted back to secants. Just make my life a little easier. I'm going to take out my tangent, and I'm going to replace my tangent using my Pythagorean identity. So I'm going to solve this for tangent squared. So I'm going to replace my tangent squared with secant squared minus 1. And as I said, this was our derivative. So that means that u is secant x and du is going to be secant x tangent x dx. And when I do that substitution in my integral, I'm going to get u squared minus 1, and then du. And then we have to distribute, of course. U to the 4th minus u squared. And then I use my power rule to do my antiderivative. 1/5 u to the 5th minus 1/3 u cubed plus c. But of course, we're not done. We have to go back to our original variable. And so 1/5 secant to the 5th minus 1/3 secant cubed plus c. As you see me work through the secant cubed, you'll understand why this is a much easier scenario to work through than the alternative when you can't actually do this. As I said, if you have even tangents and an odd secant, you want to pull out a secant and a tangent. If tangent is originally even and you pull out one tangent, this will be odd, and then this replacement that we did won't work. And so that leads us to this third scenario. Now, the difficulty with our third scenario is that we don't have really any easy way to do this with our other integration rules, with just u substitution. If I pull out a secant squared, I have only a secant left, and then I have to do a substitution to get the remaining secant turned into a tangent. Even if I were to do that scenario, I would end up with a square root with a square underneath it, and that's not an easy integral to complete. If I try to pull out a single secant, I don't have a tangent in this scenario to apply it to. And if I had even tangents, I would be stuck with an odd tangent, which would leave me with that I'm substituting and I'm introducing a radical into my problem. So the way that this is going to work is that we're going to do this via integration by parts. And in order to separate this into two functions, one which we can integrate and one which we can differentiate, we're going to separate this into a single secant to be u and a set of the remaining pairs of secants to be dv. Now, if you have like 5 secants, then you would have secant cubed here and secant squared, because secant squared is what we're going to integrate in our integration by parts. And that is just a tangent. So that's going to simplify the problem a little bit. But unlike some previous integration by parts examples you may have seen, this is going to involve both quite a bit of algebra and that looping behavior that we saw with exponentials combined with sine and cosine. So this is not an easy integral to do. So we're going to let u be secant x and dv be secant squared x dx. And that means that du, our derivative of secant, is going to be secant x tangent x dx. And v is the antiderivative of secant squared, which is going to be tangent x. Oops, no dx. Applying integration by parts, we have u and v. So secant x tangent x minus the integral of v du. So secant x and then another tangent x will make this tangent squared. Now, the way that we're going to proceed is we're going to change our tangent squareds back into secants. So this is going to then become, I guess I don't need that. Turn that into that. This is going to be replaced with solving our Pythagorean identity for tangent squared. This is going to be secant squared minus 1. And that seems like that's self-defeating, but it's actually what's going to help us break out of this. So I'm going to distribute my secant, and then we will have a problem to solve. So I'm going to copy this because that's not going to go anywhere. Distributing my secant and my integral, I'm going to get back to secant cubed of x. And in a separate integral, just secant x. Now, this integral I can actually do. So that's what I'm going to do now. I'm going to get my secant x tangent x term from the front. I am going to, and I should mention that this is actually, don't want to lose those minus signs. This is from this one integral, so this is a minus, so this will actually be a plus. And then what is the antiderivative of secant? Well, it's kind of messy. It's log of secant x plus tangent x. And then at the end, we still have our secant cubed integral again. Now, how does this help us? So let's actually put this all on one line where we started and where we ended up. So again, this is that same looping behavior we saw with exponentials and sine and cosine functions. We start out with an integral, we do some integration by parts, and we end up with the same integral expression on the other side of the equation. So what we can do is I can add the secant cubed x integral to both sides so that we can combine them. So that's what I'm going to do here. And just to make it crystal clear what is happening, that's for the next video. Just to make it crystal clear what is happening, I'm going to add this integral and that integral. So on this side of the equation, this integral is going to cancel. This side minus plus, they go away. And on this side of the equation, they can be added together to produce 2 of the same integral. And so at this point, just like with our exponentials and our sine and cosine, we divide everything by 2 in order to get our final answer. Divide everything by 2. We put a 1/2 on this one. And we put a 1/2 on this one. And an arbitrary constant divided by 2 is still an arbitrary constant, so you don't have to worry about that one. And so this is what our integral ends up being. Again, using those same ideas that we saw in the integration by parts problem, we end up with this integral that is really messy, but at least we were able to get it solved. If you have higher powers, where we got this secant that we could integrate, where did it go? Right here. You will only be able to reduce the power of your original secant by 2 at a time. And so what's going to end up happening because of our integration by parts? So you're going to end up getting a secant cubed here. You will have to proceed through the rest of the integral in order to get that secant to the 5th, which is going to pop back out. If you started with secant to the 5th, a secant to the 5th will pop back out again. You can do that, the same process, in order to combine your original secant to the 5th with the secant to the 5th that comes back from your integration steps. And so you will reduce your integral. But here, where we ended up with a single secant and we have a formula for that, you will have an integral that involves secant cubed. And then you will have to do this process all over again in order to get, or look it up in the table, to get your secant cubed integral completed. So higher odd powers of secant, you will do this several times before you end up finally at the end. So pray that you never get one of those. I did one once. I was not a happy camper. Okay, so this is how you deal with secants and tangent integrals. And again, if you have secant or cosecant and cotangent combinations, they all work the same way. That means that cosecant cubed is going to work pretty much the same way. And then the other thing to kind of keep in mind is if you have combinations of trig functions that don't meet our sine and cosine combinations, or our secant and tangent combinations, or our cosecant and cotangent combinations, or if you have more than 3, like 3 or more different trig functions in your expression, then the best strategy is to convert everything to sine and cosine and follow those rules. Okay.